9. We are working further with complex numbers. So we're going to be adding, subtracting, as well as multiplying, dividing. We will also get into i's to higher power, as well as rationalizing denominators. So the two big ideas that we want to remember today is that I squared is equal to negative 1. And anytime we have the square root of negative 1, we replace that with I. Okay? So the square root of negative 1 is I. Anytime we have an I squared, we simplify that to negative 1. So we're starting out with our complex number, a plus bi. A is the real part, bi is the imaginary part that comes together for the complex number. When I look at these, I want to be careful. This is just simply addition. I'm not multiplying here, I'm adding like terms. So I have my real number plus my real number, which gives me a positive 1. And I have my imaginary 4i and my imaginary negative 11i, which gives me a negative 7i. And I want to keep my answer in complex number form, a plus bi. All right, so if I come over here, I see that I have a minus sign. I think it's in your benefit to distribute that negative sign, almost like multiplying everything in the second set by negative 1. So I'm going to go ahead and do addition of the opposite and opposite. That way I don't lose my negative sign. I have 4 and a negative 5, which is negative 1. And then I have a negative 1i and a negative 8i, so negative 9i. All right, next set, we have the same idea. When I go to add, nothing needs distributed. 6 plus negative 6 is 0. And then I have a negative 2i and a positive 2i. So my final answer here is simply 0. Over here, again, I have subtraction. So I'm going to go ahead and distribute that sign. Make sure you change this to a negative 10 and a positive 4i. So 10 and negative 10 is 0. And then I add my like terms of 3i and 4i, and I get 7i. I am treating I in these problems just like I would treat x. It comes along like a variable. All right, so we're going to come down to this next set. We're going to talk about multiplying. And again, the reminder is anytime I get an I squared, I want to simplify it to negative 1. So here I am simply distributing the 2i. So 2i times 3 is 6i. Again, you treat I like you would treat x. 2i times negative 5i is a negative 10, but it is I squared. Now we're never going to leave an I squared here. We know that I squared is negative 1. So I have 6i minus 10 times negative 1. So I have a negative times a negative. Final answer in a plus bi form is 10 plus 6i. All right, over here we have a little more work to do. We have to FOIL this. So we're going to do our first, which gives me 20. Then we're going to do our outside, which gives me a negative 15i. Our inside, which is negative 24i. And last, which would be a positive 18i squared. And that's often a mistake, as we miss that I squared. Now I want to add like terms, and I also want to deal with I squared. So 18i squared really becomes 18 times negative 1, which in turn gives me a negative 18. So when I go to add like terms, I have 20 minus 18, which is 2. And then I have my I terms to add up. And those add up to negative 39i. Again, if you wanted to rewrite more of this, you could. I simply wanted to reduce this down to a negative 18 and lose the I squared. All right, we're going to do the same thing here, but it's important to see that these are very similar. The only difference is my sign, 1 plus, 1 minus, which creates the idea of a difference of squares. And anytime we had a difference of squares, we know that the middle terms cancel out. So I'm going to go ahead and FOIL this to see what happens. 7 times 7 is 49. The outside becomes a negative 14i. The inside is a positive 14i. And last is a negative 4, but it's I squared. So when I go to clean this up, the negative 14i and the positive 14i, they cancel out. The negative 4i squared becomes negative 4 times negative 1. Which gives me a positive 4. Remember, this is multiplication, not addition. So I am left with 49 plus 4, and I get a final answer of just 53. This is really important. It's going to help us later when we rationalize denominators, because by multiplying by this sign change, My i's canceled out, I squared became -1, and I've simplified it down to a real number. Okay, we have one more. There's nothing to distribute. We're just multiplying. 6 times 6 is 36. I times I is I squared. And since that's 36 times -1, my final answer is -36.
Yeah.
All right, to continue on your notes, we are going to work with imaginary units but being raised to higher powers. So when we do this, we know that I to the first is the square root of -1. So we would always replace the square root of -1 with I. But I to the second, we know, is -1. And that's by taking your -1, square root of -1 squared, and that gives us -1. That's how we find I squared. Now if we jump and we try to find I to the third, I'm going to use what I know. I'm going to make it I squared times I to the first. So I'm going back to my power properties. If I have a to the m times a to the n, that gives me a to the m plus n. So if I'm multiplying bases, I add the powers. So if we look at this, I'm multiplying the bases. 2 plus 1 is 3. Okay, how does this help me? Well, I squared is -1, keep I to the first. So I end up with -I. So you're going to see a pattern here. My answers are either I, -1, -I, and if you're guessing the pattern, the next one would be +1. I want to rewrite I squared times I squared to replace the 4. 2 plus 2 is 4, and so that really is -1 times -1, and that's where I get a +1. So all of these can be broken down. The only two that I need to have memorized are the first two. The square root of -1 is I, and I squared is -1. These are the two that I have to know, and then it's going to make everything else work for me. So I'm going to use another piece of paper here to help, but I'm going to take and break down I to the 5th. So we're going to do a couple of these. So I to the 5th is an odd power. So I want to write it as I to the 4th times I to the 1st. Now this is taking some effort, but the idea is anytime I have an odd power, a 5, a 9, a 13, a 7, 11, a 15, I'm going to have an extra I hanging out. I always want to work with even powers. And the reason I want an even power is because I to the 4th can be written as I squared to the 2nd. So now I'm using my power property of a to the m to the n. A power raised to power, I multiply. So I'm using this power to power rule to get multiplication. So when I have this, I have I to the 2nd, which is I to the 4th, and I still have my extra I. If I can base everything on I squared, I know that that is -1. And -1 to the 2nd will be a +1, and that just leaves me with one I, or simply I. So I to the 5th is I. All right, let's talk about I to the 6th. Well, I to the 6th is an even power. So I can break it up as I to the 3rd and I to the 3rd, or I to the 4th and I to the 2nd, but then that requires me to know a whole lot. But if I can break it down to I to the 2nd to the 3rd, I always want to keep this as I to the 2nd. 2 times 3 is 6, and I to the 2nd is -1 to the power of 3. If I'm not sure, I can put it in a calculator, but if I have 3 negative signs, won't I keep a -1 at the end? All right, let's jump to I to the 8th. So here we have a -1. Notice that this is going to come down. These are all going to be I's. These are all going to be -1s. It's following that pattern. I'm jumping over to I to the 8th. Again, there are several ways to write it. I want to base it off of I squared. So I to the 2nd to the 4th. I'm taking my power, I'm dividing it by 2. I squared becomes -1. So I'm using my fact. That's all I need to know are these two rules. And then I can derive the rest. So I squared becomes -1. -1 to the 4th, well, that's an even power, and every two negative signs cancel, so I get a +1. If I jump down to I to the 12th, I to the 12th, I want to write that as I squared to the 6. My goal is always to create an I squared as my base, because I squared turns into negative 1 to the 6. And since I have an even power, I have an even number of negative signs, I will get out a positive 1. Okay, so the even power is a little bit easier. I can jump to I to the 14th. That becomes I squared times to the power of 7. So I'm always basing it off of I squared. That's my goal. And that becomes negative 1 to the 7th. I have an odd number of negative signs, so my answer is negative 1. So the even powers are a little bit easier because I can jump right in. I can divide each of these by 2 and get my power on the outside. But when I have an odd power, I have to take off the odd I. So even powers will always be 1 or negative 1, because all of my i's cancel out. Odd powers will always have an I left over. So let's take another look at a couple of odd powers here. So if I look at I to the 9th, let's jump to I to the 9th. I cannot write that as I to the 2nd it'd be this. This doesn't help me, guys. I don't know what negative 1 to the 4.5 is. I don't want that. So what I want to do is I want to take off the odd I. So I know that my answer is going to have an I hanging out. Remember, every 2 i's, I squared is always negative 1. So every 2 i's cancels out, cancels out, cancels out, and I've got the odd I left over. So I'm going to work with I to the 8th, and it's going to be I squared to the 4th. 2 times 4 is 8. Always put a 2 in here, and then build your power. And I keep the extra I there. This becomes negative 1 to the 4th times I. So negative 1 to the 4th is 1 I. So my final answer is I. Let's do one more. We'll jump to I to the 15th. So here is I to the 15th. Again, I know that my answer is going to have an I in it. All of these are going to have an I in it because that is going to be the odd I left over. And because of the ways the powers work, we're going to have a negative I. So I'm going to rewrite this as I to the 14th times I to the 1st. I only need to take that odd I off. So I'm not breaking it down in different ways. 7 and 8, 5 and 10. I always just want one I here and an even power. And this becomes I to the 2nd to the 7th times I to the 1st. Well, this is negative 1 to the 7th times I. And negative 1 to the 7th is going to stay a negative 1I. So my final answer can simply be negative I. All right, let's jump back to the notes now that we've got our chart filled in. And let's derive these. I know there's some people who want to memorize this chart and then try to figure out what row this would be in or what column it would be in. And I think it's actually easier just to understand how to break them down. So we have an example here with a negative 3 out front, and that's just going to come along for the ride. So it is going to be negative 3, and this I to the 12th, well, we know what it is. It's going to be 1, but let's check it again. I to the 12th is going to cancel out to just be a 1 or a negative 1 because I have an even number of powers. So it would be I squared to the 6. Well, this is negative 3 still staying, and this would be negative 1 to the power of 6. Now, order of operations, you cannot multiply until you address your power. So the negative 3 is staying, and then negative 1 to the 6 is going to be a positive 1. So the final answer is negative 3. Okay, now we have I to the 25th, so it's not on our chart, but we're going to go ahead and work with it. I know, and here's the directions over here, I know that I want to break off the odd I, so I have an even power of 24. I don't get rid of it, it stays there. I'm going to break this 24 down to an I squared to the power of 12 times I. 2 to the 12th. I to the 2nd to the 12th becomes my I to the 24th. This becomes a negative 1 to the 12th times I. I have an even power, so every 2 negative signs cancel. I'm left with one I, or simply I. All right, the next idea that we're going to do with our imaginary numbers is we're going to be dividing them. But in these problems, there is nothing to divide. So we want to go back to the idea that I need to rationalize the denominator. So expressions in the simplest form cannot have square roots in the denominator. And this goes back to chapter 1. Because the imaginary unit represents the square root of -1, I can't have I in the denominator. All right? So we are going to rationalize any denominator that contains an imaginary unit. And to do this, we're going to multiply the numerator and the denominator by the complex conjugate. So let's remember what the complex conjugate is. If I have an imaginary number a plus bi, and I have a line over that, that is telling you to find the complex conjugate of a plus bi. And the complex conjugate of a plus bi is simply a minus bi. The complex conjugate changes only the sign of the imaginary number. That is it. Now, why is this useful? I'm going to take you back to the example we did here, where we had 7 plus 2i times 7 minus 2i. 7 plus 2i, 7 minus 2i, this is the complex conjugate. And when I FOILed this, my i's canceled out, and I got an I squared, which turned into a -1, and that's what happens. I was able to cancel I out. And so that's what we're going to use to help us rationalize the denominator. All right, so if we look at this first example, the complex conjugate of 8i is -8i. And so I can go ahead and I can use the complex conjugate, but it's going to give me some extra work. So I'm going to do this problem twice. I have 3 plus 7i over 8i. The complex conjugate of 8i is -8i. And if I multiply the bottom and the top by -8i, I'm really multiplying by 1. So it's the same rules we use to rationalize the denominator. So when I go to do this, I distribute it, and I get a -24i, and then I get a -56i squared in the numerator. In the denominator, I get a -64i squared. All right, so I have some cleaning up to do. My -24i is going to stay. My -56i squared is going to become a +56. And that comes from -56 times -1. And in the denominator, it's going to be -64 times -1. So my denominator is +64. Now, if you look at my three terms here, you can see that I have a common factor. In order to reduce this, I have to be able to take it out of all three pieces, and so the common factor of all three of these is 8. So I can divide this by 8, and I get a -3i. I divide this by 8, I get 7. And I divide this by 8, and I get 8. And if you're going to put it in your complex number form, it would be 7 minus 3i all over 8. Okay, so I have rationalized the denominator, but notice that I had to reduce everything by 8. When I have a single term, one term, a monomial in the denominator, I am actually able just to come in and multiply by I. I don't have to use the complex conjugate, and that saves me a little time. It's only if I have one term in the denominator. And if I do that, there's my 3i plus 7i squared, and there's my 8i squared. And if I clean that up, I have 3i minus 7 over -8. Now, these answers that I have are equivalent. The answer we had was 7 minus 3i over 8. And if you notice, all of my negative signs are the opposite. So I accept either answer. However, you'll see textbook and worksheets, they do not leave, it's not proper to leave a negative sign in the denominator. So they're going to divide everything by -1. So -7 divide by -1, positive 3i divide by -1, -8 divide by -1. So this is the answer you will often get. This answer is acceptable. You may want to rearrange it, but then we see that all of our signs are the opposite. So either answer is acceptable. Again, if I have a single term with I can simply multiply by I, and there's no need to reduce at the end. Remember, to reduce, you have to take it out of all three terms. Okay, now this one's going to take a little bit more work. if I try to multiply just by I, let me show you what happens here. If I try to come in here and use that same trick, and I'm going to have to fix this because it's not going to be right, and I come in and I say, well, I'm just going to multiply by I. It does not rationalize the denominator. The top gives me 5i plus I squared, and that's fine. But the bottom would give me a 2i minus 4i squared. Okay, so I really get 2i plus 4. So I fixed this I, but you see I reintroduced another I. So trying to multiply by just I will not work. So this is where we have to multiply by the complex conjugate. We are changing simply the sign of the imaginary number. And what I do to the bottom, I do the same to the top. That way I am multiplying by 1 and balancing it. Okay, so this takes a little bit of time. We have to FOIL the top. So 5 times 2, we get our 10. We get the outside of a 20i. We get the inside of 2i. And we get last a positive 4, but it is I squared. Now, I like to just continue with the top, so I'm going to go ahead and clean that up. 4i squared becomes a negative 4. So 10 and negative 4 is 6. 20i and 2i is 22i. So I've gone ahead, I've cleaned up my top, I've gotten rid of any of the I squareds. Now I'm going to go ahead and use my difference of squares. And I'm going to take my 2 times 2, which gives me 4. I have an outside of 8i, which is positive. I have an inside of negative 8i. And I have last negative times positive is going to be a negative, and it's 16, and don't forget the I squared. So my middle terms are supposed to cancel if I use the proper complex conjugate. And then I have a negative 16 I squared, which becomes a positive 16. Negative 16 times negative 1. Final answer, 4 and 16 is 20. Okay, now if we take a minute and we look at this, I have 3 terms here. All 3 can be divided by 2. So my final answer that I can turn in is 3 plus 11i all over 10. And I have rationalized the denominator. Remember, a rational number can be written as a fraction, repeating decimal, or terminating decimal. The square root of negative 1, which is I, is not even a real number. It's imaginary. So it's neither rational or irrational. And so that is how we rationalize the denominator and simplify it.